Welcome to Hart und Trocken. My name is Dirk Schiebon, and in this short video I want to present you 3 simple rules for differentiation. First by motivating them graphically and then by proving them using the differential quotient. In our last videos on differentiation, we have introduced the derivative of a function as the slope of the tangent to the function at a given point. The slope of the tangent is approximated by the slopes of a sequence of so-called secants, which are straight lines going through the point where we want to calculate the derivative at, which is a, f of a in this case, and some other point on the curve, which is some distance h further left or right, in this case further right. The slope of the secants is calculated as the quotient of the vertical leg divided by the horizontal leg of the so-called slope triangle, leading to this quotient. Then we let go h to 0 and watch what happens to this quotient. Plugging in 0 for h directly doesn't work because it leads to a denominator of 0 and we can't calculate the fraction. This is why the theory of finding limits of these quotients is used, because here h is a 0 sequence which actually never reaches 0. This theory of finding the limits of these quotients finally yields the right derivative of 1 for that function at point A, which is why we can draw the tangent with slope 1. So that means that finding the derivative of a given function is all about finding the limits of these so-called differential quotients. Based on these differential quotients, we will now collect some very simple rules for differentiating functions. First, we want to calculate the derivative of constant functions. It is obvious that the tangent is also horizontal, no matter where we choose the point A. So that means that if f of x equals some constant a, we have f prime of x equals 0. That means the derivative is constantly 0. We can simply prove this using the differential quotient, which is lim h to 0 f of x plus h minus f of x divided by h. And now we replace f by that constant a, such that we get lim h to 0 a. Well, minus a divided by h, and we see that this is 0. And the proof is finished. Next, we are interested in the question, what happens to the derivative of a function if we shift that function vertically along the y-axis, like this? Obviously, the slope of the tangent doesn't change, so expect the derivative of a function not to change when we move the function along the y-axis. This is our expectation rephrased in formulas. When we have a function y, which is created from some other function f by adding a constant a, we expect that the derivative of that function y is equal to the derivative of the function f. Now let's prove this using the differential quotient. So we have lim h to 0 of y of x plus h minus y of x divided by h. And that is lim h to 0. Now I replace y by the definition of y, which is a plus f of x plus h minus a minus f of x divided by h. And now we can simplify in the numerator and we get f x plus h minus f. You see both a's vanish, divided by h. And that, of course, is the definition of f prime of x. That is the proof. Next, we are interested in the question, what happens to a derivative of a function when we multiply that function by a constant? In this case, we take the function fx equals x squared and multiply it with 1.5. So you see that the tangent changes its slope from 1 to 1.5. So it is increased by the same factor. And we can proceed multiplying the function by 2, and the slope of the tangent is also multiplied by 2. This is also the case for different positions of the point A. For instance, here we have the function 0.5 times x squared and the tangent has slope 1. If I multiply the function by factor 2, we see that the slope of the tangent is multiplied by factor 2. So our expectation is the following. Whenever we multiply a function f by a constant factor a, the derivative of this function is also multiplied by this factor a. Again, we want to prove this using the differential quotient. So we have lim h to 0 of y x plus h minus y of x divided by h, which is lim h to 0. And now we replace y by the definition of y, which is a times f of x plus h minus a times f of x divided by h. And now we can factor out the constant a and put it in front of the fraction. So we get lim h to 0 a times the fraction. And now we may apply a rule for the limit. That means we can distribute the calculation of the limit on the two parts of this multiplication. These two parts are a and the difference quotient. So we get lim h to 0 a times lim the fraction. Well, and obviously the lim of a is a, and the lim of the fraction is f prime of x times f prime of x. And the proof is finished. So this is the summary of the simple rules for differentiation we have just understood. That's it for this video. Thanks for watching and see you next time.